Welcome my friends, welcome to my next lecture. Now in my last lecture I was talking about the definitions of curves, smooth curves, piecewise smooth curves. That means what is called if I have a curve which say I have a smooth curve, if I make a finitely many pieces, and if each piece is smooth, then this is called piecewise smooth curve, or sometimes I will say that this is contour. Okay, so then I was talking about the orientation. So my plan for today's lecture is to start once again what is the meaning of orientations, that means the natural orientations. Contour I have already discussed, and then I will talk about the main kind of point of today's lecture is to talk about what is called contour integrations or line integrations. Once I have that one, you will see to define a contour integrations I need the notions of what is called Riemann-Stieltjes integral, and then I will talk about path independency and Cauchy-Gussac theorem. So I will start with the notions of natural orientations, and then I will go on. Let me see how far I can complete for today's lecture. Okay, so as I said, so let me start with the orientations, that means the natural orientation. So if I have a curve, say smooth curve or piecewise smooth curve, then what do you mean by like natural orientation? That's what I have written. Look, see, natural orientations of the curve induced by parameterizations. Now if I have a curve, of course it will have a parameterizations, that means it will be a map from some interval subset of R2 complex numbers, right? That interval either should be closed and bounded interval or in the full real line. And then you will see once I have a curve, it will automatically give orientations. I already discussed this kind of things in my last lecture. Again, I am just recalling this part. Look, suppose this is my curve. Okay, so what is this? So let gamma be a curve with my parameterizations. Gamma is equal to zt. That means z is a map from closed interval ab to c, right? And it is a curve. Smooth curve means my curve is, of course, what is the definition of curve? That means it is a continuous functions. Differentiable curve means it is differentiable. Smooth curve means it is differentiable along with derivative is continuous. So therefore you assume that your curve is smooth, so that means your curve is differentiable, derivative is continuous. So therefore if I have a curve with my parameterizations gamma is equal to zt, then look, if t increases, now this is actually t goes to z of t, this kind of map you will have it, right? Now I will have A, I will have B. Now if t starts from A and moves towards B, then you will see that z of t will start from z of A, and as t runs from A to B, then ZA will cross along the curve and approaches to the point ZB. So therefore now if t is equal to A, that means I will have the point ZA, right? Now if t is going from A to B, then my point z of t moving from ZA and approaching to z of B, so it will go in this way, and that will give a natural directions. That means I have to start from ZA and I have to go along the curve and I will reach at ZB, and that directions is called the natural orientations or natural directions. Okay, so that's exactly I have written. So as t increases from A to B, the point z of t moves continuously. Continuously means if I have a smooth curve, that means my curve z of t is differentiable, derivative is continuous. So therefore the point zt moves continuously from ZA to ZB in the specified directions, which I indicate by drawing arrows along the curve. This directions is called the orientations or natural orientations of the curve induced by the parameterizations z of t. Okay, so therefore what is the orientations of a curve? So if I have a curve, it will have a parameterizations, and say let it suppose the parameterizations for the given curve say either zt or gamma t, whatever it is. Now if t runs from A to B, then my point z of t starts from ZA and end with z of B, and it will have a natural directions, and that natural directions I will say that natural orientations. For example, this is the corresponding natural orientations. Similarly here, so I have a curve, this is actually closed curve. So if I start from ZA, then if t runs from A to B, then I am moving in these directions according to my parameterizations, and that is actually the what is called natural orientations. So that's what I have written, orientations of the curve induced by parameterizations. Simple closed curve. So if I take a curve which is simple closed, then what do I mean by positive orientation? That is sometimes give some problem, I'll start with okay, let's assume that gamma is a simple closed curve with a positive orientation. What does it mean? Simple closed curve I have already explained. What do I mean by positive orientations? Orientations I already said. So if I have a curve and if I have a parameterizations, it will automatically give a natural orientations. So what do I mean by positive orientations? The definition is the following. So let gamma be a simple closed contour. I already discussed what do I mean with that. Suppose it will have the parameterization, say gamma is equal to z of t, which is xt plus it. T runs from A to B. So therefore it will automatically have orientations or natural orientations. Now if gamma is parameterized so I need the orientation in such a way, so if gamma is parameterized so that the interior bounded domain, so this is, suppose this is my curve, okay, this is my curve, so suppose I am starting with ZA and suppose I am moving in these directions and end up with ZB, because it is simple as well as closed, so therefore there should not be any cross, and ZA is equal to ZB because this is the definition of closed curve. Simple means there should not be any cross. So suppose this is my curve, then what I demand is that if gamma is parameterized in such a way, so that means it will automatically give a orientation, and that orientation has some special properties. What is that? If gamma is parameterized so that the interior bounded domain of gamma is kept on the left as zt moves around gamma, then we say that this orientation is positive or counterclockwise or anticlockwise. Now you can see, so now I am starting from ZA, right? Then I am moving in these directions. So that is the parameterizations. I have the parameterization in such a way, suppose I am starting with ZA and I am moving in these directions because of the parameterizations or natural orientations. Now if I move in this direction, you see this is the corresponding domain which is bounded domain bounded by my simple closed contour. This is the interior one and this is the exterior one. But you see, if I move along in these directions, this interior bounded domain always in the left hand side, from my left hand side, and in the right hand side I will have the exterior, that means unbounded domain. So therefore if I start with a simple closed curve with a parameterization, so that if I move along the curve in some directions, of course the directions will be specified by the parameterizations, and if these things happen, what that means, if I have the interior bounded domain, if I move along the curve, the interior bounded domain always in my left hand side and exterior unbounded domain will be always in the right hand side. If the curve has this kind of orientation or directions, then I will say that this is actually what is called positive orientations, or sometimes I will say that this is counterclockwise or anticlockwise directions. One example is that suppose I will have a circle gamma of t which is 2 cosine t plus I sin 2 sin t, t runs from 0 to 2 pi, this is actually oriented what is called positively. Positively means, now look what, this is very nice. For example, what is that? So this is, you can write it, this is 2 times e to the power it, right? So that means 2 times cosine of t plus I sin of t, that means it will be a circle of radius 2. So then suppose I have a circle of radius 2. So therefore this is my point 2, 0. Now what is my parameterization? This is my parameterization, t runs from 0 to 2 pi. Now if t is equal to 0, then what is the value of gamma of 0? This is should be 2, that means 2, 0, this is the 1. And if gamma is equal to 2 pi, that means it is also will give you 2, right? That means I am starting from this, then I am moving in these directions, and end up with what is called 2. So okay, you can say that, okay, how do you ensure that if I start from t from 0 to 2 pi, it will be in that directions? Look, t from 0, it will have this value 2, 0 or 2. Now if I take t is equal to pi by 2, let it be, okay, then what is that? Then gamma of pi by 2, what is the value? This should be 2 times cosine of pi by 2 plus I 2 times sine of pi by 2. What is that? So this is 0, so that means this should be I times 2. That means I am actually reaching this point. So therefore I am starting from this point, I am reaching here. So that means I am moving in these directions. Similarly, if I put t is equal to pi, you will end up with this point. And if I have t is equal to 2 pi, then it will have this point. And if I take t is equal to, so 3 pi by 2, so if I take t is equal to 3 pi by 2, then you will have this point. So therefore if I am starting from t is equal to 0, that means I am starting from here. Then I am moving in these directions. Now if I move in these directions, look, the interior bounded domain, it is always in the left hand side. So therefore this is left hand side, and exterior bounded domain, it is in the right hand side. So that means this is the corresponding what is called positive orientation. So I draw a picture. So suppose this is my curve, okay, simple closed curve, and suppose I have given this kind of orientations. So now if I move along my curve in such a way so that interior bounded domain always I am having in the left hand side and exterior unbounded domain in the right hand side, that means I am saying that that orientation is called what is called positive orientations. Okay, so this is what I am written. Of course, if it is in the opposite direction, that means I will say that this is the negative orientation. Negative orientation means what? So I will have the orientation or directions of my curve in such a way so that if I move along the curve, in the left hand side I will have the exterior unbounded domain, and in the interior side I will have the interior bounded domain. If these things happen, that means in that case I am moving in this direction. Suppose this is in this direction. So in the left hand side, I will have unbounded one and bounded interior one in the right hand side. So if it is in the opposite direction, then I will say that I am talking about what is called negative orientation. Okay, so therefore simple closed curve, that is the negative orientations. Look, so same thing. So suppose I am having this kind of curve, then I am giving the negative orientation. That means I should move along my curve in such a way so that the interior bounded domain should be always in my right hand side and exterior unbounded domain should be in the left hand side. If I have that kind of orientations or direction, then I will say that this is a negative orientation. So, okay, so let gamma be a simple closed contour with parameterizations gamma is equal to zt, which is xt plus I yt. Then I am saying the definitions. If gamma is parameterized, show that the interior bounded domain of gamma is kept on the right as zt moves around gamma. So that means if I have zt, so that means if I move around my gamma, that means the interior bounded domain always in the right hand side. Now if I move in this direction, you will see in the interior bounded domain is in the right hand side. Then we say that this orientation is called negative orientations or clockwise. You can say that I am moving in the clockwise directions, or the other one is the anti-clockwise directions. So example is this one. Now you can guess what is that. So now earlier I was talking about circle with the kind of this one, like 2 cosine t plus I times 2 sine t. So this is t from 0 to 2 pi. It will have what is called positive orientation. Now look at here. What is it? So this is also a circle. You will see this is also a circle. But so look, so what is that? So this is, you can write it. This is actually, so this is you can say that, okay, I am doing it here. So this is what? Gamma of t, it should be e to the power I times minus of t, right? Where t runs from minus 2 pi to 0, right? Correct? So therefore if t is equal to minus 2 pi, so this is what? This is cosine t plus I sine of t. This is cosine of minus t plus I sine of minus t. What is that? This is cosine of t minus I sine t, right? Now either you can just draw the picture. So what is that? It will give a circle, right? It will give a circle, unit circle of radius 1. Now if starts t is equal to say minus 2 pi, then what is the value? T is equal to minus 2 pi. That means gamma of minus 2 pi, it should be what? This should be e to the power, also because of definition, this should be cos of minus 2 pi minus I sine of minus 2 pi. So this should be what? This should be cosine of 2 pi plus I sine 2 pi, and sine 2 pi is 0, so therefore this will give you 1. So that means I am starting with the point 1. Now I am starting from minus 2 pi and then I am approaching to 0. So therefore I am starting from here and then suppose I am going here, I am going there. Now let me just take the value at gamma is equal to minus pi. Okay, then what is the value? This should be cosine of minus pi minus sine of minus pi, right? So what is that? This should be cosine of pi and this is 0, right? So this should be 0. So what is the cosine of pi value? So this should be minus 1. That means it should be here, minus 1. So that means I am starting from here, then as t runs from minus 2 pi, then you will have minus pi and then 0, then I am moving in these directions. Okay, correct? So therefore now if I have this circle gamma of t, this is the corresponding parameterizations. If t runs from minus 2 pi, I am starting from here. If t is equal to minus pi, then I am reaching here, and again if t is equal to 0, I am end up with the point 1 comma 0. That means I am moving in these directions. Now if I move in these directions, then look, in the right hand side I have the interior bounded domain, and in the left hand side I will have the exterior unbounded domain. So therefore this is the corresponding what is called this orientations. It's actually the what is called negative orientations. Now this also you can think about in this way, because this is nothing but, this is the curve. Of course, this is a curve, means it's a unit circle. Now this is nothing but the negative of this curve, e to the power I t, t runs from 0 to 2 pi. So this is a unit circle, t from 0 to 2 pi. Now if I draw a orientation here, you will check the orientation is positive orientations. That means if I have these parameterizations, it will induce our orientations which is actually positive. That means I should move in this direction. That means the interior bounded domain is in the left and exterior unbounded is in the right. So therefore this is positive orientations. Now if you remember this, if I have gamma, then this is nothing but minus of gamma actually, the way its parameterization is given. This is actually minus of gamma, this one. Now if gamma has some orientations, minus of gamma I already talked about. If C is a curve, suppose which will have some orientation, then minus of C which will have the orientation in the opposite direction. So that means if C has a positive orientation, minus of C will have a negative orientation. That exactly going on. So gamma of t, that means it will have a positive orientation, minus gamma, which is nothing but this one, will have a what is called negative orientation. Okay, so that's what it is. Okay, so this is kind of some observations. It says that, so if a simple closed curve C is positively oriented, okay, just now I have discussed, then given a curve C, I already discussed what is the meaning of minus of C. So if C is a curve which is starting from some point, say if C has a parameterization z of t, so that means if C is a curve starting from ZA end of ZB, then the what is the minus C is the, that means it traces out the same set of points, but instead now it should start from ZB and come back to ZA. That means if C is starting from ZA to ZB, minus of C will be the same set of points in the curve, but in that time it will start from ZB and come back to ZA. So that means if C is positively oriented, then minus of C will be negatively oriented, right? So that's what I have written. So suppose I am starting from here and I am moving in these directions, then what is my minus C? It will be starting from here and it should be in the opposite direction. So opposite direction. So therefore a positively oriented contour, this is negatively oriented. If C is positively oriented, then minus of C is negatively oriented. If C is negatively oriented, then minus of C is positively oriented. Okay. Now there is a default case. What is that? So if the orientations or parameterizations of a simple closed curve C is not given, suppose you do not have any, suppose I give you some problem, and suppose I didn't mention anything about the orientations. So then it is always understood that the simple closed curve C is oriented positively. That means you choose the parameterization in such a way so that it should be oriented positively. Okay, so that is the by default case. Okay, so in some problem, if I didn't mention anything about the orientations or anything about the parameterizations, you just choose the parameterizations, or by default it is given that my curve C is positively oriented. Okay, so now I am done with what is called curves, differentiable curves, smooth curves, piecewise smooth curves, or contour. Then I have the orientation, positive orientation and negative orientations. So now I discuss very little bit about the contour. So now I am in a position to talk about what is called line integral or contour integral. So that means what I will do, so if I have a functions f from D subset of C to C, and suppose I have a contour, say some contour, so suppose this is my D, right? So this is my domain D. This is Z plane, right? And it is a map, you will have a W plane, right? So therefore I have a map, right? Suppose if I take some kind of closed contour here, suppose with some orientation, right? Then I will define what do I mean the integrations over this contour gamma fz dz. So this is the meaning. Now to do that, I need to just recall the definitions of what is called Riemann-Stieltjes integral, and then I will have it. So okay, I have written. So the integrations of f which is defined on some domain D subset of C over some piecewise smooth curve. So you have a domain defined, if you have a functions defined on some domain, in that domain take a piecewise smooth curve or contour, then I want to define the integrations of f over this piecewise smooth contour. Now just recall, if you are comfortable like with if you are comfortable with what is called multivariable calculus, you people have done this kind of integrations before, which is called vector line integral. That means if I have a functions f from some domain D subset of R2 to R2 over some oriented smooth curves, there are also similar kind of definitions will be there. Then this kind of notations you might have seen. Okay, so integrations over gamma. Gamma is a some smooth curve sitting inside D. Then the meaning of this kind of things. Now there you see, since I am dealing with R2 to R2, so what is this functions? Capital F of RT, that is also an element in R2 because F is a map from R2 to R2, and then R prime of t, you can see, so the RT is actually the parameterizations of my smooth curve. That means R is a map from some closed interval AB to R2. So therefore t goes to R of t is actually element in R2. So therefore in particular, if I start with nice curve, smooth curve, that means my R is differentiable, that means R prime of t, it will also be an element in R2. So therefore this object f of RT, so this is also in R2. So therefore the meaning f of RT times R prime t, that means it is actually the dot product. So that means f of RT is an element in R2, dot product with R prime of t. So therefore now this map t goes to f of RT dot R prime of t, it's a scalar valued functions, and then this integrations, if you remember, it is the parameterization, since gamma is the smooth curve and RT is the parameterization, this is exactly equal to A to B. This functions, if I say this is my function g function, so this is gt dt. And this is the integrations you know. If g is a nice functions, continuous functions from closed interval AB to R, because this is dot product, it will give you a scalar, right? So therefore you know the integrations of these things. Now when I will talk about line integral or contour integrations, actually this kind of things I will like mimic the similar kind of definitions that you know, what is called vector line integral, that will be, but this time like here actually I am talking about dot product, because in R2 I will have the usual dot products. So therefore in that case this is the make sense, but when I move from R2 to C, now C is a field, that is a corresponding scalar multiplication of two complex number is there. In this way I will make sense of my line integral or contour integral. Okay, so but before that you will see, so I'm a kind of contour integration, since I am talking about the integrations of my f over some contour, then you will see the Riemann integrations you know, so you have to you need little bit more than that Riemann integration, that means Riemann-Stieltjes integral. That means this kind of integrations you know, integrations a to b fx dx, that you know, but to talk about what is called line integral or contour integral, I need a little bit more. That means I need Riemann-Stieltjes integral. What does it mean? That means I want to give sense of integrations fx and d say nu x. But what is that? So this time nu is a function of bounded variations. I will explain what do I mean by function of bounded variations. Now in particular, if I take nu x is equal to x, it will get back to your what is called Riemann integrations. So now I need to have the notions of what is called Riemann-Stieltjes integral. That means if I have a nice functions f, now I would like to give a meaning of the integrations of f with respect to a functions of bounded variations. If I take eta x, that function of bounded variation is exactly equal to x, then it will get back to your what is called Riemann integrations. So first I will explain what do I mean by functions of bounded variations, and then I will give I will recall the definitions of Riemann-Stieltjes integral. Once I have the notions of Riemann-Stieltjes integral, then I will talk about line integral or contour integral in terms of this Riemann-Stieltjes integral. Okay. So before that, let me just very briefly talk about functions of bounded variations. What is the definition of function of bounded variations? It says that you start with a complex valued functions defined on closed interval a to b, and suppose you take a partitions of your interval a to b. Suppose p is equal to a is equal to a small x naught less than x1 up to xn is equal to b. It is a partitions of my closed interval a to b, be a partitions. Then I am talking about the variations of f with respect to that partitions. What is the meaning of that? So you have a functions defined on closed interval AB taking complex valued. Then I'm considering a partitions P of my interval A to B. Then I'm defining a number which I'm saying is that variation which depends on my partitions. What is that? So this is the sum from I from 1 up to n f of xi minus f of xi minus 1. That means you have a partitions, you have the point finitely many points x0 x1 up to xn minus 1 xn. Then what you do, you take the difference f of xi minus f of xi minus 1, take the modulus and sum it up, I from 1 up to n. So this will be the what is called variation of f with respect to my partitions P. What is the absolute? Now this time my f is taking complex value, so therefore this is modulus of the complex number. Then I am saying that the total variations of f, which is defined as, well, in different book has different notations, but I am saying that v suffix v a to b, that means a to b, or a and b is the interval of the definitions of functions a, v a b of a. What is that? Now each partitions I'm talking about the variations of f. That means if my partition changes, the corresponding number will change. Then what I am doing is that you consider supremum of all the partitions. So that means you take as many partitions as you can. So that means take any partitions, consider the variations, and you take the supremum. Okay. So then that I am saying the total variations, where the supremum is taken over all partitions. Then I am saying that my functions f is said to be functions of bounded variations if this supremum is finite. Okay. So that is the definition of functions of bounded variations. That means start with a complex valued functions defined on closed interval AB. Take a partition P of the interval AB, define a variations of my functions f with respect to that partitions by this formula. Then if I changes my partitions, my variation will change, and then you take the supremum of all those partitions. I will say that my functions is a functions of bounded variations if this supremum is finite. For example, if I take f of x is equal to x functions, you can check it, this supremum. So what will happen? Look, see, if I take f of x is equal to x, then what is this object? What is this object? This should be what? So you can just have it, so you can calculate it. So suppose I am considering the functions. So I am considering the functions from AB to R, right? So I am considering f of x is equal to x functions. Okay. If I consider these functions, then what will happen? Look, so this is exactly equal to I from 1 up to n. F of xi means what? This should be xi minus 1, right? Correct, and this is the absolute, but this is my partition, so that means xi minus 1 is always less than xi because of this. So therefore it is actually will give you sum over I from 1 up to n xi minus 1. This is positive. Then what will happen? This is what, this sum will, that cross term will get cancelled. This is telescopic sum. So what we will have, you will have xn minus x0. And what is xn? Xn is nothing but b, and x0 is nothing but a. So therefore this sum is always give you b minus a, irrespective of the partitions p. So that means whatever partitions I will take, this is variation is always b minus a. So therefore supremum is b minus a, which is finite. So therefore this is a function of bounded variations. So there could be many. Oh, this is very simple. So that means f of x is equal to x. This is a function of bounded variations if I take a functions from AB to R. Okay. So once I have a functions of bounded variation, okay, there are many, for example, monotone increasing functions, you can take it. This is also a function of bounded variations. In fact, a functions of bounded variations, you can break it in real valued functions, difference of two monotone functions, and complex valued means you can have real part, imaginary part. Each real part is a function of bounded variation, imaginary part is a function of bounded variations. Real part I can break up into difference of monotone functions. Imaginary part, that is also a functions of bounded variation. Real valued, that also have a difference of monotone functions. So therefore any complex valued functions of bounded variation I can make up into 4 pieces, and each of them are monotone. So in that way you can think about it. Okay. So this is very little. I am not saying very kind of in details about functions of bounded variation. I am saying that suppose you have a functions of bounded variation, that means the definitions I have given, one examples I have given, and there are plenty of examples, but then I will say that what is the meaning of the Riemann-Stieltjes integral of integrations of f with respect to functions of bounded variations. Okay. So suppose you have a function, since I am talking complex valued functions, so which is of the form u plus ib, this is u is the real part, v is the imaginary part, then this is, one can prove it, if f is a functions of bounded variations, then u and v, these are actually real valued functions, this is also a real valued functions of bounded variations. Okay, one can prove it. Now this is like informations I need it, because later on you will see it will have a connections. It says that if gamma is a piecewise smooth curve, piecewise smooth curve I already talked about, that means it is a contour, right? So it will be a smooth curve. In fact, it is not smooth fully, but I can break my curve into finitely many pieces, and each pieces are smooth. So therefore if gamma is a piecewise smooth curve, then gamma is a function of bounded variation. One can prove that. Not only that, if I calculate the variation or total variation, which is nothing but the integrations a to b absolute of gamma prime t dt. So this is, these integrations, you know, these are real integrations, na? So this is real valued functions, and I am talking about the Riemann integrations. So one can prove that if gamma is a piecewise smooth curve, then it is a function of bounded variations, and not only that, total variations you will have by this kind of formula, a to b absolute of gamma prime t dt. I am not going to prove it, but you just one can take it as an exercise and prove that. The way I have proved, if I take f of x is equal to x, its variation is exactly equal to b minus a. Its variation is exactly equal to b minus a. Similarly, one can prove that. It takes some effort to prove that if I have a piecewise smooth curve, maybe just to prove functions of bounded variations, it is okay, then you can have it like so that supremum is finite, that maybe you can prove it like with some maybe easily you can prove it, but to have that its variation is exactly, that means supremum is exactly equal to this one, that needs little bit of effort. Anyway, I am not going to discuss that part, but you just assume that if I have a gamma which is piecewise smooth curve and gamma is a function of bounded variation, then its variation, it turns out to be exactly the integrations of gamma prime t absolute dt. Okay. Yeah, so I think I should stop here. So now I have defined functions of bounded variations. Now in my next lecture I will discuss what is called Riemann-Stieltjes integral. That means if I have a nice functions f, say complex valued functions, then I will make sense the integrations of my f with respect to a functions of bounded variation. Once I have that one, then I'm in a position to talk about the definitions of line integral or contour integral in case of complex valued functions of complex variable, where if I take any piecewise smooth curve or contour inside my domain, then I can make sense integrations over this piecewise smooth curve gamma fz dz. I think in my next lecture I will start with Riemann-Stieltjes integral, and then I will introduce the notions of what is called line integral or contour integral. I think I should stop here. I will start with Riemann-Stieltjes in my next lecture. Thank you.